talking about the physics of baseball today. So this is one of my introductory slides. This is yet another. The World Series is coming up. When we scheduled this lecture, we didn't actually know how it would come out. But I was actually said today would be a great day because I was anticipating just a slightly different outcome. But nevertheless, we love baseball, and it's a great sport, and there's a lot of physics in it. So let me just ask, starting at the top, if you will, how many people are here because they love physics? Just wondered, you know? How many people are here because they love baseball? All right, so I think we're in the right place. Are there any professional or former professional baseball players? College? Coaches? High school? One of these. High school baseball players. Little league baseball players. That would be me. Okay. Great. All right. So, so this is the field. And there are a few rules that have to do with the size of the field that affect the game. This is the professional game, the college game. One of the things that's pretty interesting to me is that it's a square that's turned in an interesting way. It's called a diamond. It's 90 feet on a side. And if you do the math, you get this line across the middle is about 63.6 feet. Yet the pitcher's mound, for reasons that are historical, many things that happen in culture and science happen partly for historical reasons, is 60 feet 6 inches away. So that's a pretty important number because that's where every play in baseball starts. In baseball, like many American sports, the energy is released in short bursts, right? And then we wait, and that's why sports commentators in the U.S. Have a different kind of job, unless it's hockey, for example, where the action is fairly straightforward. Okay, so that's the basic layout. I think we know that. Here's what we're going to talk about today. Where is the physics in baseball? This is actually just a quick quiz for you. I'm going to talk about the human limitations a little bit, some of the more obvious ones. Then we'll talk about pitching, hitting, and some of the technology. There's a lot we won't talk about, but there are questions. So physics of baseball is not just for fun. And certainly it can help you enjoy the game more, I think, to understand and see some of the physics. But there is real scholarly literature. People are really doing research at universities and laboratories. NASA finds a great interest in educating the public using baseball as an example. So I just have a selection of papers here, how to hit home runs. Okay, so that's something every baseball player should read. It's in the American Journal of Physics. The dynamics of the baseball bat collision, corked bats, juiced balls, and the like. Catching fly balls in virtual reality. This is a really interesting problem to try to figure out actually how it is that outfielders can track a ball and in a few seconds get to where it lands most of the time. The motion of an arbitrarily rotating spherical projectile and its application to ball games was written by some Australians. And I was trying to figure out why the Australians were so interested in this. And you might think it's because what's the sport they play in Australia? Yes?
Yes, I mean, the answer is because they just are.
They just are, that's right. It's scholarship. And of course there's cricket, but a lot of this article is about baseball, the spin of a batted baseball. And you can even do a graduate thesis on it. Washington State University Department of Mechanical Engineering actually has a sports science laboratory. Several other universities do, Penn State, the University of Mass at Lowell, et cetera. And actually I've drawn on some of their work for this. Anyway, so here's my question for you. To start with, what forces matter most in baseball? I'm serious. Okay. Gravity, yes. That's pretty good. That was actually my first. Gravity, air friction. Okay, let's see. Friction, good. Did you read these slides beforehand? Personal experience, right. Friction. You got to grip the ball, you got to grip the bat. He mentioned air friction, which is a manifestation of viscosity. Air is a fluid. Any others come to mind? Rotation is indeed extremely important. I don't classify that as a force. It's a part of the motion, and we'll discuss that. Certainly couples, for example, to viscosity. Spring force and modes, right. So let's call that elasticity, all right. So that's extremely important. So these are elastic forces, right. So these are some of the things that we're going to keep track of here today. So you did very well on that quiz. Here's something else. All right, let's see if you can do this. A 90-mile-per-hour pitch, all right, travels, it's 55 feet. Remember I said it was 60 and a half, right? Why is it 55? Well, you'll see Verlander here, where he releases the ball is at least 5 feet. So actually, in the scholarly literature, 55 feet is used as this distance, first of all. All right, so it's 55 feet to the plate. How long does it take? You guys did the calculation that fast. Okay. Well, I thought I'd sort of help you do it, but you're right, so I can go through this fairly quickly. All right, it's 90 miles per hour. That's 132 feet per second, right?
So it's fairly basic, 5/12 of a second.
I see. Or 55 130 seconds of a second, right? Which is 0.42 seconds. Right. So that, you're right, it's less than half a second. It's 0.4 to half a second typically. All right, so how far does it fall? Gravity, everybody noted, I think we all agree, is the most important force.
1 meter.
Right, so, well, I guess, how do you answer this question? In this forum, one thing you could do is just draw in what you've seen in baseball. But I am emphasizing fall, which means that I wanted to do what physicists tend to do, which is start by limiting our consideration to gravity alone. All right, that's reasonable. And if we do, some of you may or may not, this is actually maybe the only serious equation here. 1/2 AT squared and 1/2 GT squared. So if you think way back or not so way back, depending on your age, to the last time you had a physics class, this one sticks with a lot of people, I know that. And G is what we sometimes call the acceleration of gravity. That is 9.8 meters per second squared, or 32 feet per second squared. Half of 32 is 16. You square this and you get 2.8 feet, or about 86 centimeters. Okay, so meters is about right. So that if it's just gravity and it's 90 miles per hour all the way through, so that's where we start. So we sort of have an idea, 0.4 of a second, about a meter it dropped. But that's pretty simple. We already know that. Okay, the 90 mile per hour pitch, well, there's air resistance. There's drag on the ball, so it slows down. And when we always saw the 95 mile an hour pitch or 100 mile an hour fastball or something like that, that's the starting speed. That's the maximum speed that it has. Right when it leaves the pitcher's hand, it slows down. And that's because of air resistance or drag. The ball is spinning. And as a consequence of a spinning, it curves in many different directions, and that's what makes a pitcher have an advantage over the batter. Right? 2/3 of the time, the batter does not, or more than 2/3 of the time, the batter does not successfully hit the ball one way or another. But the spin of the ball, just like the speed of the ball, is slowing down. All right? So that makes it even more complicated over that 0.4 of a second as the ball goes from the pitcher towards the plate. And how far does it fall? Well, that's rather complicated. But this, of course, is all physics. It's just more complicated. So we're going to understand some of the complications. All right. So let's take a look. This was near the end of the American League Championship Chupp series. I think I can find a way to play that again. Okay, here we go. That's the 4/10 of a second. And boy, he missed that. All right, what was he thinking? All right, well, he was thinking, I didn't react correctly, right? That pitch really fooled me or something like that. So how long is 4/10 of a second to us is a question I'd like to explore, and I want to explore it by having you take part. Okay? And so to do this, we're going to do some reaction time measurement, and I have some helpers here. We're going to get some of these yardsticks out into the audience. And look, you have to get involved, which means some people, I don't have enough yardsticks for everyone, but those who are interested in measuring the reaction time should stand up, okay, now, and then we'll give you a ruler unless you already have it. And but you need a partner as well, okay? So if you're interested in your reaction time, stand up. I'll give this about a little bit of time. All right. Anyone interested? You guys are going to do it. Good. Okay. So you all ready? We have enough people, I think. Okay, so here's how we do it. I guess I need a ruler as an example. Okay. So we got to measure a time. And the time we're going to measure is the time it takes the ruler to drop a certain distance, and you're going to react. So here's what we do. The partner of the person whose reaction time we will measure, nice sentence, will hold the ruler, okay, up, poised to drop it. The person whose reaction time is being measured will put their fingers over the 30. All right? And without any cue whatsoever, without a countdown, without warning, the ruler will be dropped, and the victim will grab the ruler as soon as they can and measure the distance, right? So that means you have to subtract a number 30 from 30, okay? So you could do this maybe 2 or 3 times. It does take, you want me to do it for you? All right, here you go. 30. Okay, open your fingers. And when once I drop it, you close it. Grab it with this hand. Move that hand away. You ready? Yeah. Your right hand. Good. You ready? All right. And so that number was 17. You had 13 as your score. All right? What do we get? All right. Yeah, in just a sec. No, they can hold them, actually. We'll use it again. All right. If you have a number that if you have your number, go ahead and sit down. You can keep the yardsticks for now.
Maybe kind of an average?
Yeah, kind of an average. Not yet. There's a reason, but I forgot what it was. Okay. It's all right. It's okay. All righty. So, yeah, how do we convert this to a time? We have a distance. We convert it to a time. Well, I said this was the only equation you'd see, but you're seeing it again. Air resistance, spin, none of that really matters very much here. So here's the equation. The distance it dropped is 1/2 gt squared. And if we measure d in inches, and I'm going to explain why it is that we're doing this in inches, because you might be surprised. This is the formula. The time is the square root of 2 times d times 384. Don't worry, I have a table in just a moment that will help you make that conversion. Yeah, so we're using yardsticks instead of meter sticks because you can go to the hardware store and get yardsticks for 50 cents a piece. And meter sticks, for some reason, are more expensive because they're imported from Europe. So we use inches. But that's fine because, as you know, baseball is a game of inches. All right, so here's a table. Okay, do you remember, if you remember your number in inches, let's say it was 6, then it's 0.177 seconds or 177 milliseconds, all right? So everybody who did this measurement, you got your time? All right, so let me just ask for a show of hands. How many people less than 100 milliseconds? Which is, less than 2 inches. You have to drop it yourself to get that. All right. How about 100 to 150? Anyone? 150 to 200. So a significant number of hands. 200 to 250. So about the same. 250 to 300? Still about the same. So it's sort of a broad range. And over 300? Not many. Okay? So that's pretty good. So we got 150 to 200, 250, an average of about 200 milliseconds. Half the time it takes the pitch to get there, it took you to react. Okay, so this is, of course, quite relevant. So now you know, and this is, if you need for some reason to, I'd suggest maybe you keep one in your car. If you need to demonstrate the reaction time is pretty good at any point. All right, actually, I'm going to come back to this, but here's what goes on during that 200 milliseconds, okay? One thing is that since your partner hadn't told you, you have to notice that it's falling, right? About how long does that take? Well, don't worry about that yet. We'll come back to that. But once you notice, you have to tell your fingers to close. And once you tell your fingers to close, the nerve, it has to travel along nerves about a meter from your brain to your hand. And finally, you actually have to do it, which takes some strength, okay, muscle strength. So that first one, the visual response, how long does it take you to respond? Well, that's an interesting scholarly question. It's a subject of quite a bit of research, but we can do that. What I have, I don't know if can we turn those lights off briefly? Great, okay. What I have here is a blinking light. So a strobe light, that's right. Do you think it's possible to turn those off? Yeah, I'm a little worried about that, but we'll be okay. That's blinking about 5 times a second. Can everybody tell it's blinking? All right, good. All right, so I'm going to speed it up. And, basically at some point it becomes a blur. You can't distinguish blinks. Your brain is telling you it's not blinking anymore. All right, so basically I'm going to turn this up, and people, as soon as you think it's a blur, yell stop. All right? Faster and faster and faster. Stop. Okay, I'm going to go a little further. Stop. Keep going, stop. All right. But certainly there, right? All right. So the point is, thank you for the lights. That's great. Okay. Oh, yeah. So I saw how fast that was blinking. You couldn't see. But that was blinking about 30 times a second, which is not surprising. Televisions and before all this modern technology of flat screen TVs and computer monitors and things like that, generally refreshed about 30 times a second because that was just fine for us.
Wasn't it 60 hertz power line?
So 60 came on as later on. Certainly computer monitors, you've seen 60, 70 and things like that. But 30 hertz refresh rate is also used. And the reason is that that's good enough. And 30 times per second is 30 milliseconds, basically, 33 milliseconds. So if we include that here, this time. 190 is about the 200. This is I do this whenever I can with classes, with groups, with physics of baseball lectures and so on. And the number is right around 200, just like you, so it's very typical. 30 milliseconds of that is just how long it takes your brain to respond. It's how long it took you to tell that if it were more than 30 milliseconds between flashes, you could tell they were distinguishable. You don't know this necessarily, but many people do. It's about 100 meters per second is what it takes the nerves, and it goes about a meter, so that's 10 milliseconds. So 30 plus 10 is 40. Most of that time is actually how long it took you to close your fingers. You just can't do this too fast. Okay, that's just pure muscle strength, and what distinguishes most top athletes from just below top athletes like you is of course this specific training, muscle strength. There's a lot of things that go on to the technique of batting, but that is some fundamental limit. Okay, so that's the reaction time. Now, pitching. Sorry, okay. Yeah. Pitching. So watch this pitch. Nasty. That's the term they use. And it's a technically very accurate term. It totally fooled Damian Jackson here, I guess. So what's going on? Why is the bottom dropping out of this pitch, as the commentators would say, as they show this over and over again? And, well, all those things that we discussed. What makes the bottom drop out of this pitch? Well, let's just understand a little bit about what's going on. Okay, first of all, the pitch leaves the pitcher's hands, in this case about 80 miles an hour. So that was a slider, I guess. So it has a velocity forward. It's going through air, which is kind of a wind, all right? Pushes back on it. We call that drag. And that's opposite the velocity. Make sense? And, all right, so that's part of it. It slows down. So as it slows down, instead of just having the arc of a constant forward velocity as it slows down, it will drop a little bit faster towards the end of its flight, first of all. So that explains part of the drop alone. So gravity pulls it down. Pardon me? We do. More to do. All right, anyway, so there's, of course, gravity, as you said. It's the most important point. Now, the spin of the ball is pretty interesting. It creates lateral forces. So a typical fastball has basically backspin. So I can draw it in this picture. A slider, the axis of the spin for backspin is right out of the page towards you, right? So the ball's spinning just like this. But different pitches, that axis is rotated. But this one we can understand. So this is backspin. And the surface of a baseball is rough, and the baseball has stitches on it, okay, and they're red, which is helpful, at least for what we're looking at. So as a consequence, mostly of the roughness and so on, the baseball, as it's spinning, drags air with it. Right? So the air gets dragged with the baseball. That's called a boundary layer. And so that air is spinning with the ball. And what I want you to notice is here at the top of the ball, the boundary layer is going in the same direction as the wind the ball feels. And at the bottom of the ball, it's going in the opposite direction, right? It's going to the right. So at the top of the ball, there's greater speed of the wind than there is at the bottom of the ball. Okay? And there is a physics effect. It's basically the Venturi effect. When you combine forward motion with spin, it's called the Magnus effect. And what this does is it has the effect that when the speed is lower, the pressure's higher. Okay? It's an airfoil. And that's the same reason that an airplane wing has lift, that there's a slower speed of the air at the bottom of the wing compared to the top of the wing. More pressure at the bottom and at the top pushes it up and gives it lift. So a fastball, which is mostly backspin, is a ball that doesn't follow the path of gravity. It follows a path, actually, it doesn't fall as far. Now I have a demonstration here just of the airspeed effect, the Venturi effect. Okay, so, and it's kind of cool. So if I blow the air from this hairdryer, you can do this at home, right? Okay. As long as you have a fairly frictionless surface, all right? Now you would think that if I blow on this side, which way would it go? Left. I'm getting some lefts. I'm getting some rights. How many lefts? How many rights? Okay, let's see. Okay. The people who say right must think that the air over here is pushing it that way, right? The people who say left heard what I said. All right. And if I do it on the other side, the reason being that the air moving fast here reduces the pressure on this side, more pressure pushes it that way. Okay. So if it's spinning and moving, we get lift in this case. And of course, if the axis of rotation is different, then the lift, I'll show you that when we talk about a batted baseball a little bit later. But then what's called lift here is in some funny direction. It pushes the ball. For example, what would happen if we just completely rotate the axis of spin so that the ball is spinning around a vertical axis? Okay? What will happen to that is a curveball. I have kind of another demonstration that's just related to this Venturi effect, so I think I'll do it now. It's noisy, but basically in this case, a little bit different from baseball, but nevertheless it's really cool. A little bit different from baseball is that the air will be going around both sides of this ball fairly fast, and so the ball is actually going to seek a place where the forces balance on it. Somewhere around there. Anyway, that's another sort of manifestation of this same thing. Right? So it's obvious that you can produce significant forces. In fact, in baseball scholarship, these forces are measured in their relationship or proportion of gravity. Okay, and the other thing is that the spin slows down, so all these spinning effects change as the ball moves towards the plate. So you can really get an amazing thing. Now, this, I guess this is another equation, but one interesting thing about baseball is that all these effects of drag and things related that are consequences of drag depend basically on the velocity of the ball, the diameter of the ball, and the characteristic of the ball going through the air, which is the viscosity. All right, so these things matter. This thing is called Reynolds number, so if you want to sound really cool, you can say, well, we've got to consider the Reynolds number. So we have to consider the Reynolds number. For a baseball, this is the drag coefficient, the way in which the drag depends on the velocity of the ball. The larger this number, the more drag there is for a given velocity or Reynolds number. But baseball actually takes place here where you'll notice that this curve is very flat. So it's really pretty interesting that baseball has sort of tuned itself somehow to be a sport where at least this is a little less complicated, though we could deal with this, certainly, with real calculations. So this is a result of things. Okay, so here's this picture again, but I wanted you to note that different kinds of pitches have different initial speeds, different spins, axes. The curveballs are not around the same horizontal axis, and the slider and so on. As fastballs, the one I demonstrate is basically a fastball. This is the time that it takes. Okay, so it's about 1/10 of a second difference between a fastball and a curveball. All right, that's that's 20%. And if you don't know, hitters kind of recognize this along the path of the ball. But if you don't know whether it's a fastball or a curveball, 1/10 of a second is way more than the time the swing takes. So That's why you can look really fooled. If you don't, that's why they call it fooled. You don't know what kind of pitch it was. And you certainly can't judge the speed of the pitch at the rate at which it's coming to you. That's very difficult to do. This is what the drop would be without any aerodynamic forces, just gravity alone. Okay, a slower pitched ball will have a larger drop, right? Okay, it takes longer to get to the plate and longer to drop. These are the aerodynamic effect on the drop in the ball. For a fastball, it's actually upward in feet. And for curveballs and sliders, it's downward, and so the total drop is anywhere from about 1.5 or 2 feet for a fastball to all the way down, and it basically hits the plate, or very near the plate for a good curveball. This is all affected by the grip, okay? And almost all affected by the grip. So these different grips, the baseball players among you may have learned one or more of these grips. I once had a baseball that actually told you where to put your fingers. But it was for a right-handed pitcher, so I couldn't use it. Actually, I couldn't even throw the ball when I put my fingers in the right place. All right. And even the knuckleball is kind of interesting. People probably know that the knuckleball essentially has no spin, so it's the raised stitches that determine what's going on. The boundary layer is different. It can spin every which way. And in a moment, I'll show you sort of a different example. So it's not just the grip. This is a slider. This is actually the pitch I showed you before that totally fooled Jackson from the phantom cam, as Fox calls it, point of view. So you can see the grip on this. Actually, let's just take a look at this broken down by frame. It's pretty interesting. So these are the frames of the video, but I have them here. Here it is, just leaving his hand. You can see the stitches on the ball. I don't really think, I don't know if it's been confirmed, but there probably aren't any, and if there are, very few batters that can actually pick this up, though there are urban myths about that at least. Okay, so it's just left his hand. You saw how his the motion of his arm. This ball is actually going to the right of the plate and will curl off to the left. So it starts out with an initial horizontal velocity that would take it right towards the batter, basically. Okay. Look at the spin on the ball. The way we'll do that is going to the next frame, and the next frame, and the next frame, and so on. So you can see that the ball is spinning. It's got backspin on it, but it's also spinning around a vertical axis. And off it goes. This is a little slow doing it this way, but okay, bye. Good. All right, this doesn't just happen in baseball. Okay, bend it like Beckham is a real thing. Watch the bend on that ball. Okay. Now, soccer is interesting because the soccer ball keeps changing. I don't know if you know this, but the World Cup ball this year was rather different. It had quite a lot more. It had 50 stitches on it. And the 4 years before, there was a new ball made by Adidas for the World Cup that was much, much smoother. And it turns out if the ball is too smooth, this boundary layer doesn't exist. And the curving of the ball actually can be the opposite of the example that I gave you. And that actually has driven some of the players crazy. So, because their technique, and they practice this, and this is really an intentional bend on the ball. Their technique is based on, practice. So if the ball changes, the whole thing changes. In baseball, as you know, every 3 pitches or so, there's a new ball. Because anything that happens to the ball other than just smoothly landing in the glove of the pitcher or catcher will change the ball, which changes the game. Right? So that's the reason. You don't want a scuff ball. It also happens in tennis, as you know. This is Federer. And watch, what kind of spin is he putting on that ball? That's top spin. Why do tennis players do that? Tennis players do that because if he hit that ball at 100 miles an hour that went over the net, it would go way over the end line. And by putting top spin on it, instead of lift as there is on a fastball, it drops. And so it drops way below gravity, the normal path of gravity, and that's why he can whack the ball so hard and keep it in bounds. So let's go to hitting. Okay, so this is a simple picture of what happens in hitting, and it's fairly accurate to start with. What we're going to do is go into a special frame of reference, which we call the brick wall frame, okay? And so it's actually the frame of the ball hitting the bat, okay? So imagine that's the bat, but the bat's so heavy compared to the ball that it just bounces off it. And if this is an elastic, what we call an elastic collision, a collision where in which case the ball would come in with a certain velocity and it would recoil with the same speed but the opposite direction, that's all. Okay? So that's where we start with the ball-bat collision. Now the bat is moving, I'm left-handed, so the bat is moving forward at a significant velocity. So we have to transform that into the playing field frame, or the laboratory frame, as physicists like to say. So that's the same picture, but now we take all that and move it forward, and now we have to add to this speed of the ball the velocity of the bat, or the speed of the bat. So that means the ball moves away at, you just add those two velocities together, and it's typically 100 miles per hour, which is 44 meters per second. So I have a nice little demo of that. It's only slightly dangerous to the people in the front row. I was asked about that at the start. So be ready. Yeah, I guess I forgot this one. All right, so this is at least heavier than this. So this is my model for the baseball. This is my model for the bat. And I'm going to create a collision of these two. Actually, only they're going to move together when I drop them under the force of gravity. All right. But when this hits the ground, it's going to recoil, and this hasn't started yet. So not only that, but the tennis ball is much lighter than the basketball. So let's see what happens. All right. Anyway, that's the principle in your frame of reference. Good. So double ball bounce is my cue for that. Next. All right, so apparently it's all about bat speed, right? So let's take a look. This is a swing and actually tracking the speed of different parts of the bat. Closer to the pivot point, the radius is smaller, and as the bat rotates with essentially a constant angular velocity, as we say, or constant rate of swing here, closer to his hands, these are closer together. They're all the same time, so that indicates, compared to the outside, that this part is moving slower than that part, right? That's pretty clear, right? If you're going to get hit by this, you'd rather get hit by the inside than the outside. So we should hit the ball off the very end of the bat, right? You would think so, because that's the highest bat speed. But there's more to it. Or as I say, or is it? Okay. So first of all, let's refine what we're thinking about. This is a collision of a baseball with a thing. The baseball is a bit elastic. It deforms quite a lot and then springs back. All right. And the question that we ask in physics about elastic collisions is the kinetic energy of the ball, or the speed of the ball, the same coming in as going out? What do you think? No, not at all. And that's because some of that energy goes somewhere else. So the collision is not elastic, it's inelastic. The scientific term for what we study is called the coefficient of restitution, and it's basically how much the ball recoils of the initial speed, or actually speed squared, or energy. You know, so here's a baseball, and it's an official league baseball, and the way we measure this is simply dropping it, okay? And if we drop it from this height, this is 75, 50, and 25% of the height. I'm making a mess here. The question is, how far does it come back up? Okay, sort of shown here. So with a baseball, let's see if you can tell me. You know, it's about 30%, maybe not even. This is a racquetball, 75%. So if this matters to you, play racquetball. Golf ball, any guesses? Pretty good. You know, the best actually is this steel ball. Nope, not that one. The worst is the steel ball. Ping pong ball and super-ish ball. All right, anyway, that's the way we measure it. Called the coefficient of restitution. It matters what the ball is hitting. The steel plate's a pretty good example, and in this little clip here, that also is a steel plate that's used for that. So here we are, the coefficient of restitution. It's, as you sort of hopefully saw, we should get about 30% for a baseball. So that's a big loss in energy. When we do a ball-bat collision, measurements show that it's about 50 to 55% depending on the nature of the bat. Here's a laboratory experiment that actually measures that. It's fine to have a stationary bat. We don't have to do the experiment in the moving bat frame. And so this is a device that was developed at the University of Illinois by Alan Nathan to make these measurements by propelling the ball forward and then making that measurement. So an inelastic collision, there'll be a quiz afterwards, so make sure you got this right, that the energy of the ball ball-bat combination is reduced by the amount of energy that goes into other forms. Basically, it appears as heat, though momentum is conserved. So you can do the math. So that's one of the complications. Here's a simple calculation. It really just uses the 1/2 GT squared, which is hidden in here, to calculate if the ball does leave the bat at 100 miles per hour. Actually, I pulled this slide from a lecture I give to the seniors in physics. So, at any rate, it has some angle above the horizontal. We need to know what that is, and so there are two components of the velocity. We learn in physics to separate the x and y motion here. If we don't consider any of the aerodynamic forces, we find that the ball should go 694 feet, and they don't go that far. Because we know. I mean, you shouldn't be surprised. Why do I bother? All right. Well, here is the same picture, but this picture is now moved to the batting, the batting frame. The ball is leaving the bat with some velocity that's not horizontal. In fact, it doesn't actually leave the pitcher's hand quite horizontal, but nearly so. Okay, so that just means that the so-called lift vector is not vertical. Gravity is always downwards, and drag is always opposite the velocity. This shows you, actually, I have to just cycle through this. It's an incoming ball, hits a bat, and then you can see just as it moves away that it's got backspin on it. And that's a great way to do a home run swing because you actually give the ball some extra lift with backspin. Okay? So here's what a real trajectory for that 100-mile-an-hour ball looks like. Instead of looking like this and going out to 600 feet, they typically go, 400's actually pretty good. There's a spin on the ball, usually, that's not just vertical, so you can see if an outfielder were running for this ball, the ball would keep, as they sometimes say, tailing away from him or her. What a drag. There are ways to calculate this. They involve all sorts of things, the humidity, the air temperature and things like that. But maybe, for me, quite interesting, because we have a family of Red Sox fans, actually, or David Ortiz fans at the very least, is his last year's set of home runs are shown here, where they would have landed if they actually went all the way back down to the ground. Mostly they don't, right? They end up in the stands or something like that. And kind of the speed off the bat, which you can see is pretty typically around 100 miles an hour. Okay, the elevation angle is around 30 to 35 degrees. And the distance that they go is plotted here. So that's hitting. One more thing about the ball-bat collision is the sweet spot. Many of you knew that you shouldn't hit the ball off the end of the bat. This is where you should hit it. Okay? So this is a beautiful hit by Marcus Goodrow. Just a great line drive. It's just a thing of beauty. And so it's worth seeing a few times. This is not the sweet spot. Okay. This is inside of that, so let's see what happens. All right. The bat vibrates horribly. So we have done some research on that here in preparation for this lecture, and that basically to understand the sweet spot. So what you saw, I guess I should show it one more time since it's just so inducing, is, sorry, really set that bat vibrating. Now I'm in trouble. Okay. Backwards. There. Okay. So what these brilliant people, Monica and Matt and Warren, have done for us is set up an experiment where we can actually investigate the vibrations in the bat. Okay? And this is an oscilloscope trace, which is just measuring what essentially a microphone or transducer here is measuring as I hit the bat in a few different places. All right. Now, the first place I'm going to hit the bat is around the sweet spot. So that's simulating the ball-bat collision, and I think, okay, so every time I do this, you see I hit it a little harder. But I'm going to try to do it the same every time. Okay, so that's what we get. Okay, so the wiggles are the vibrations in the bat that come from that. It's why you can hear that. Can you hear it? All right. Actually, I've got a hammer somewhere. Sorry, thanks. So this is going to totally mess this up. But just in case, that's the sound you're used to hearing. But it does about the same thing. So the hammer helps. All right, now I'm going to hit the ball, hit the bat about where we saw it in that video. Okay, so take a look at the screen. Okay. Much more energy is going in, obviously, right? There's much more motion to the bat. That means much more of that energy is going into the bat. If I hit it off the end of the bat, okay, and back to the sweet spot. Okay. So what a difference. And that is one of the reasons for the sweet spot. I have one more. This is not video, really, so you can keep doing what you're doing, but I just want you to listen, all right, to the difference in sound as I move from the end of the bat to the sweet spot to this. And what I like to do sometimes is have people tell me when to stop. But, but don't do that yet. Let me just give you some. Sorry. You hear the differences? All right, so tell me when I hit the sweet spot. Right around there, right? Nice, huh? That is why we go to baseball games, to hear that sound. Okay. There we go. So these are actually end of the bat that we took earlier. End of the bat, sweet spot, and middle of the bat things. Okay, so here's what's going on in the bat. Okay, these are called modes of vibration. And the top one is the lowest frequency mode. It's 200 hertz, and it's called the fundamental. This is a higher mode, which is 670 hertz. This is 1252. We'll leave it at this. But what's really interesting is that relative to the bat, the zeros of these, if you hit here, you're not on the large excursion part of either of these graphs. Here they are drawn here along the bat. All kind of coincide at this place that we call the sweet spot. So if we hit it here, we will excite these modes of oscillation much less than the others. We have this demo here, which is not a bat. It's a string, but it's exactly the same principle, and it really kind of illustrates, if nothing else, how the very basic ideas in physics just translate to even complicated things like the baseball. So this is the fundamental mode of this string here. It's a little bit hard to find. If I wanted to make this a higher mode, what should I do with the rate of the motor, of course? You speed it up. That's right.
You multiply by powers of 2.
All right. I'll try to do that. Okay. See if I can hit that one. Oops. All right. So I guess that's about right. Good. And I can go to the next one, you see, and so on. So these lowest 3 modes, the bat is not a string held at 2 ends. It's got an interesting shape that affects this a little bit, but the basic idea is still there. All right. So that's a thing. There's one more physics principle, which is, I did the standing waves, which, this is our not so sweet spot, sorry. I do have one more thing to show you, which, okay, so here's where it's being hit, and this is the fundamental way that the bat bends. All right, so here's one hit off the end of the bat. This is Marco Scudero again, who hit that beautiful line drive that we looked at. But he's hitting off the end of the bat here. What happens next? Yeah. So, whoa. Now, how did you know? Okay. Yes, the bat breaks. So there we go. Okay, so that's when we hit off the end of the bat here. And not only does the bat break, but the bat is less strong where it's thinner, and they tend to break there. Okay, so the last point of the bat-ball collision that I want to make is here, which is what we call the coefficient of, the center of percussion. And this is something that mechanical engineers learn about, and we teach in some of our physics classes and things like that. So this also tells us that if you hit a bat in various places along the line of the bat, and it's being held here, okay, there's a pivot point, right? Pivot point's where it's being held. I can hit the bat in various places, and there's a special place where the bat won't be rotating, it'll just translate. So if the ball hits the bat there, then instead of kind of rotating and requiring more strength in the wrists of the hitter, it'll just translate. And so I guess what we're going to try to do, I'm going to use this because it's big enough so I won't miss. Okay, so it's about right. Okay, so I'm just going to swing the bat, okay, so to speak. And if I hit the bat kind of right at the right place, it wiggles a little bit. I'm going to try to find more of the right place in just a sec here. But before I do that, I'm going to hit the bat down near the end. See how much it's wiggling? And it's always easier to do it in the wrong place, right? I'm ready. Okay. Now I'm back to trying to get it close to the center of percussion, which is about a little bit higher. Thanks. I need my coaches. All right. It's all about coaching. Okay, so there was the right place to do it. That's called the center of percussion, and that's obviously right around there as well. So it all conspires to make it right. Okay, so one more time, that beautiful hit. He did it all right. Okay, so I'm going to finish up here by talking a little bit about technology. Okay, baseball fans, raise your hands. All right, I don't know if you've watched baseball on the internet, but it's the least expensive way to do it because it's free. And if you look on your phone or iPad or tablet or whatever it is, you can pull up Game Day and watch a game. And it's pretty amazing what they will show you. They show you the strike zone. They show you where a pitch goes, and if you click on the right thing, they actually give you the trajectory of the pitch. And the trajectory of the pitch is cataloged in various ways. They can measure the speed of the pitch. This is all done with 2 cameras, one of them slightly behind home plate and one over by first base. and they take only 60 frames a second. So in that 400 milliseconds, they're taking around 30 frames of this, and they can analyze and computers crunch the data within a second and produce or so and produce these pictures for you, where it came, what the pitch speed was, criticize the umpire, of course. That's controversial, and what the trajectory of the pitch was. So that's a pretty amazing thing. You might wonder how it is, and if you've been listening to, say, baseball radio broadcasts for quite a long time, in the old days it used to be fastball or a curveball or a changeup. And now we have all these new names: slider, inside-out slider, curveball, changeup, etc. In fact, some of these things are listed here. Not even fastball, but fastball, four-seam fastball, two-seam fastball, cutter, which is a kind of fastball, different breaking balls, curveballs, and changeups. And then there's a knuckleball. So actually, how do they do it? And the answer is that this kind of data has been crunched. And knowing what the pitch actually was by drawing sort of two what we call correlation plots of the break on the ball, which was just this number here, how fast it goes above a straight line drawn from the beginning to the end of the path. And, oops, wrong direction. And the speed of the ball, or the trajectory in 2 dimensions of the ball. There are clusters here that correspond to these different kinds of balls. Now, apparently, this is actually used now by the broadcasters to quickly determine four-seam fastball, etc. And certainly is used by game day to give the labels that it used. So that's one example of technology. In the old days, there was nothing more than this, which is a radar gun, and at least in all, I mean, we've gone to sort of minor league baseball games in particular. It's really fun because there are all the scouts back there doing this on every pitch for a pitcher and things like that, and then writing it down. And that was the technology. I'm not going to tell you much about this, but of course it's what the police use as well. But I'm very interested in how technology is changing the game and the coaching. And it turns out, if you want to answer that question, it's mostly the scouting that uses this technology. This data is purchased by the teams. This set up in every major league park, and so they can do that. Okay, this system was developed by this company called Sport Vision. The system for pitching is PitchFX, which is a purchased software product, by the way. But just so you know, they do other interesting video things like put the lines on the football fields. So it's not the same technology. So final quiz. All right. Let's see what we think. Aluminum bats, right? We have an aluminum bat here, and it's kind of a remarkably different sound. That was the sweet spot here. That's changed the game too. What's the big deal about aluminum bats? Anybody? Okay, yeah. They don't break as easily. All right, good. I heard lighter. You say?
They're more elastic.
Right.
Just adding to that, they're more elastic, but they also have more. They're more resonant.
That's a good and bad. They're more elastic, which means that the energy doesn't turn into heat as fast, but actually more of the energy goes into sound. Right. So here's my answer. They're lighter. It's your answer, right? There's actually a larger sweet spot because of the way the modes correspond, but there's more vibration, and you gain not so much, but it has made a difference in the home run rate. Okay, so the physics of baseball. I think it's fascinating, amazing. It is changing the sport with the scholarship and so on. The research by the NCAA into aluminum bats, for example, is being taken seriously by the NCAA. And it is a very fun way to teach physics. There's a number of great examples that we can use. I hope you saw some of them there. There's so much more. We didn't talk about fielding. I got a lot of emails when people knew heard about this lecture, and people were telling me what I might talk about. I decided, but here are some of the suggestions I got. Fielding was one of them. Base running, corked bats, we won't go there. Physiology, human levers, injuries, as Brad mentioned at the outset, which I didn't want to talk about, performance-enhancing drugs, safety. All right, so it's just a whole lot of things that we could find physics in and give many, many more of these Saturday morning physics things. So I want to thank the demo lab people and a wonderful set of demonstrations that helped me make some of these points, and the Saturday morning physics staff and physics department. Martine has sustained my interest in baseball for decades now. Jeremy Kelk is on the U of M baseball staff. He came from the Detroit Tigers and is their video person, explained to me some of the technology and the way they use it. All of you who are Saturday morning physics supporters, and all of you, thank you very much. And play ball.